Deep in the Antarctic interior, the air holds at 40 below zero. A 12-vehicle convoy crawls across 1,200 kilometers of ice, hauling supplies to research stations so isolated that rescue is not an option. At these temperatures, diesel gels in the lines, steel turns brittle, and conventional trucks seize within minutes. Yet these machines keep moving, not because they overpower the cold, but because every system on board was engineered to survive it. How humans built snow trucks extreme enough to defy conditions that destroy ordinary vehicles. That story starts with a single equation. Every snow truck that survives the polar interior does so for one reason: it spreads its weight wide and flat. The essential tool for judging these machines is a single equation. Pressure equals weight divided by area, or P equals W over A. Ground pressure is not just a number, it is the difference between gliding over snow and sinking to a halt. Take a 10,000-kilogram vehicle, about the size of a loaded supply truck. On standard road tires, each tire supports a quarter of the weight. At a typical inflation of 300 kilopascals, each tire presses down with about 24,500 newtons. That gives a contact patch of just over 0.08 square meters per tire, or roughly 0.33 square meters total. Rounded, that is 0.4 square meters. The result is a heavy, focused footprint that punches through soft snow almost instantly. Switch to low-pressure snow tires running at just 80 kilopascals. The same load now spreads out over a much larger area, about 0.31 square meters per tire, or 1.24 square meters for all four. Industry handbooks and field tests confirm for a 10-ton truck, the real-world value is about 1.2 square meters. The pressure drops and the truck floats instead of digging in. Tracked vehicles go further. With a pair of tracks, each about 0.58 meters wide and 3.2 meters long, the total contact area approaches 3.7 square meters, rounded to 4 square meters as cited in classic engineering manuals. Now the same 10,000 kilograms are distributed so thinly that the machine barely dents the snow. These numbers, 0.4, 1.2, and 4 square meters, are not just trivia. They are the lens through which every snow truck's design must be understood. In the world of extreme cold, survival is not about raw power, it is about how gently a machine can step. Bruce Nodwell's workshop north of Calgary was never quiet. In the early 1950s, oil companies and government surveyors needed a way to reach drilling sites scattered across Canada's frozen muskeg and tundra. Nodwell's answer was a machine that ignored the brute force playbook. Instead, he built a vehicle that spread its weight so wide it barely left a mark on snow. The Nodwell Carrier's secret was its tracks, each nearly 75 centimeters wide, running the length of the chassis. Every track shoe sat on its own leaf spring, independent from the others. This let each section flex, pressing gently into the snow without punching through. Field engineers measured ground pressure as low as 0.15 kilograms per square centimeter, a number that meant the Nodwell could haul up to 10 tons across powder and slush where trucks and sledges failed. But the real leap was not just the tracks. Nodwell's modular chassis let teams swap out engines, cabs, or cargo beds in the field. If an oil camp needed fuel one day, a drill rig the next, or a rescue pod in a blizzard, the same carrier could be reconfigured in hours. Hydraulic steering, unheard of in off-road vehicles at the time, gave operators precise control on twisting riverbanks and icy slopes. Proof came in the winter of 1955. Oil crews loaded 3 tons of pipe onto a Nodwell and set out over 120 kilometers of unbroken snow. The carrier made the trip without bogging down once. Logistics costs dropped by 30% compared to traditional sled convoys. Word spread fast. Within a decade, Nodwell's design became the template for Arctic exploration, mining, and even military supply runs. The machine did not overpower the North. It adapted to it, showing that in the world of extreme snow, success comes from learning how to step lightly. The Soviet Union faced a unique recovery problem in the 1960s. When Soyuz capsules returned from orbit, their landing sites could scatter across thousands of kilometers of frozen forest, tundra, or drifting ice. Helicopters were often grounded by storms or distance. The only way to guarantee a crew's survival was to send a vehicle that could reach anywhere, no matter the terrain or weather. The ZIL Design Bureau answered with a class of machines that treated redundancy and range not as luxuries, but as the baseline for survival. The ZIL 4906 prototype, built in 1959, was the first Soviet vehicle engineered specifically for remote rescue in the Arctic and Siberian interior. Its three-track layout spread weight across a wide base, keeping ground pressure at just over 4 pounds per square inch, enough to glide over deep snow and thin ice. Instead of a single engine, engineers installed 2 independent power plants, each driving its own track system. If one failed, the other could keep the vehicle moving. Trials on the Kolyma River ice recorded a maximum range of 800 kilometers at a steady 30 kilometers per hour. The ZIL team logged every kilometer, measuring fuel use, track wear, and the ability to cross pressure ridges and half-frozen rivers. Even when a track was deliberately disabled, the ZIL 4906 limped home under its own power. The ZIL E167, tested in 1963, took these ideas further. With a V8 diesel engine and an even lower ground pressure, it could haul up to 12 tons across shifting permafrost. Its articulated chassis let it climb ridges and pivot across broken ice, a necessity for Soyuz recovery teams who might need to haul a capsule and its crew out of a snowdrift hundreds of kilometers from the nearest road. These machines were more than technical marvels. They were a statement that in the Soviet North, the only vehicles that mattered were those that could be trusted to keep moving, no matter what failed. The lessons learned in these trials would shape the next generation of heavy-lift polar trucks, as the needs of missile logistics and deep field science demanded even greater scale and reliability. At the Minsk automobile plant in the late 1960s, engineers faced a new challenge: build a snow truck that could move not just supplies, but entire missile systems across Siberia's tundra. The result was the MA's F-43, a platform that redefined what heavy mobility could mean in the polar world. 8 axles, each with its own set of massive wheels, spanned the length of a vehicle nearly 12 meters long. The entire chassis rested on a foundation designed to keep ground pressure under 4 pounds per square inch, less than the weight of a person standing on a snowshoe. To achieve this, MAZ engineers did not just add more wheels. They engineered a triple redundant steering system so that even if 2 circuits failed, the vehicle could still turn. Hydraulic lines were routed in parallel, not in series, minimizing the risk of a single leak sidelining the entire machine. The drivetrain split torque across multiple differentials so a broken axle would not strand a convoy. In field trials, the MAZ 543 was driven 800 kilometers across mixed snow, ice, and thawing muskeg without a single catastrophic failure, an unheard-of feat for a vehicle with a 30-ton payload. Every component was built with fault tolerance as the baseline. The cab could be swapped for a command module or a cargo pod in a matter of hours. Fuel tanks were doubled and cross-linked, ensuring a steady supply even if a line froze or ruptured. Engineers at the MAZ factory described the platform as fail operational, capable of losing major systems and still completing the mission. This was not about brute force or oversized engines. It was about spreading risk as carefully as weight, trusting that in the deep cold, the difference between success and disaster is how many backup plans are built into the steel. The MAZ 543 became the backbone for Soviet missile mobility and polar logistics, setting a new standard for what extreme snow trucks could endure. Snow vehicles face a defining choice: tires or tracks. This decision shapes their reach and resilience in the harshest terrain. Engineers measure the difference in flotation, sinkage, and traction, metrics that decide whether a machine glides or bogs down. Low-pressure tires, used from Siberian oil fields to Antarctic convoys, run at just 5 to 8 kilopascals. That is barely above a bicycle tire, but it spreads the load wide, creating a contact patch up to 1.2 square meters for a 10-ton truck. On soft snow, this keeps ground pressure around 0.15 kilograms per square centimeter, enough to keep heavy vehicles afloat. Yet, when it comes to pulling power, these tires typically reach a drawbar-pull ratio of 0.35, meaning the truck can tow a load equal to 35% of its own weight before losing grip. Tracks, as seen on the Nodwell and Soviet ZIL, take a different approach. Their contact area can reach 4 square meters, dropping ground pressure even further. Tracked vehicles on powder snow often achieve a drawbar-pull ratio of 0.45, a clear advantage when hauling freight across deep drifts. Tracks minimize settlement, sometimes sinking just a few centimeters under full load, but the balance shifts on wet or slushy ground. Here, the flexible tread of low-pressure tires can outperform tracks, displacing water and reducing suction that would bog down a rigid chassis. Decades of field tests and sinkage curves reveal these trade-offs. Tracks dominate on soft, dry snow, while tires reclaim the lead in thawing or saturated conditions. Those numbers, 5 to 8 kilopascals and a pull ratio of 0.45 versus 0.35, mark the limits of polar transport. Every mission weighs these boundaries, choosing the system that will float, grip, and keep moving as the surface changes. On the polar plateau, a truck's weight is only half the story. When the ground turns from smooth snow to fractured ice, the real test is whether every wheel or track stays in contact. Articulated chassis designs, those with a central pivot between rigid frames, were built to answer this challenge. Instead of forcing the entire vehicle to move as one stiff block, articulation lets the front and rear sections move independently, adjusting to the surface beneath them. Imagine a truck crossing a ridge of broken ice. In a rigid frame, one axle climbs while another hangs in the air, leaving wheels spinning uselessly. But with an articulated joint, the front section can rise over the ridge while the rear pivots down, pressing every tire or track firmly into the snow. The result is continuous traction, even as the terrain heaves and drops beneath the machine. Field data from Arctic expeditions show that this pivoting action can cut peak axle loads by as much as 30%. On the ZIL 4906, a 33-degree yaw at the joint allows the vehicle to snake through ice ridges without lifting a wheel. Canadian Nodwell carriers, using a simpler hinge, managed up to a 25-degree pitch, enough to bridge gaps and keep moving when rigid sleds would bog down or tip. In Antarctica, modern articulated platforms like the piston bully M400 are equipped with hydraulic cylinders at the joint, maintaining precise control over pitch and yaw. These systems keep axle loads balanced, reducing the risk of sudden sinkage or rollover. This engineering isn't just about surviving obstacles, it's about making sure that every part of a heavy vehicle can adapt in real time to the chaos of polar terrain. Articulation turns the landscape from a series of threats into a set of manageable challenges, letting snow trucks maintain their grip long after simpler designs would be stranded. In these moments, flexibility becomes as essential as flotation, and the ability to bend without breaking defines the machines that last. Antarctic convoys rely on more than just clever weight distribution. Every kilometer across the plateau is a test of hidden systems designed to keep fuel, fluids, and batteries alive in temperatures that can drop below -40 degrees Celsius. Diesel, the lifeblood of these machines, will gel solid at -15 degrees Celsius if left untreated. To prevent this, Fuel is blended with low freezing point additives and kept in insulated tanks, heated to around -15 degrees Celsius. Before each run, the fuel passes through filtration units warmed to nearly 80 degrees Celsius, melting any wax crystals that could choke an engine. Even with these precautions, maintenance logs from US and Australian programs document emergency filter warm-ups when unexpected cold snaps hit, incidents that drove a redesign of filter heaters in 2015. Hydraulic systems face their own battle. Standard mineral oils become syrupy or even freeze, so crews switch to synthetic fluids like ISO VG32, which stay fluid at -50 degrees Celsius. Gearboxes and differentials are filled with similar synthetics, each chosen for its ability to resist crystal growth and keep moving parts lubricated. Metal components such as frames, joints, and suspension arms are built from low-temperature steel or aluminum alloys, sometimes preheated to over 150 degrees Celsius before welding to avoid brittle fractures that can snap a chassis in half. Batteries are another weak link. Ordinary lead-acid cells lose most of their charge below -40 degrees Celsius. Modern fleets use lithium-ion modules housed in insulated, actively heated boxes, drawing about 30 watts to keep their chemistry alive. Cabin heaters, powered by diesel auxiliary units, keep the interior above freezing, often 5 degrees Celsius or more, so crews can rest and work without risking frostbite. Every convoy includes a dedicated recoverer, a smaller tracked vehicle loaded with spare parts, winches, and its own power supply, ready to rescue any truck that stalls. Redundant fuel lines, dual filters, and split hydraulic circuits are standard. In this world, reliability is engineered from the inside out, and survival depends on systems that most people never see. 12 vehicles crawl across the Antarctic plateau, each playing a role that no single machine could cover alone. At the front, a Caterpillar 707F tractor, riding on low-pressure tires nearly 2 feet wide, pulls a sled stacked with fuel bladders and insulated food containers. Its size is imposing, but its true strength lies in how softly it presses into the snow, delivering 35 tons of cargo over ground that would swallow a standard truck whole. Behind it, a pair of piston bully E-Series snowcats, each on broad, articulated tracks, handle the terrain where the snow turns thin and blue ice lurks just beneath the surface. Their tracks flex and shift, distributing weight so evenly that even a crevasse-riddled stretch becomes passable. At the rear, a Mercedes Unimog, fitted with winter tires and an insulated cabin, serves as both scout and lifeline, shuttling crew and equipment between the main convoy and distant science camps. Every kilometer, telemetry pulses back to base. Engine temperatures, fuel viscosity, GPS position. The convoy moves at just 5 kilometers per hour, but in these conditions, speed is irrelevant. What matters is that every vehicle finishes the journey. With each day, the cold deepens to -40 degrees Celsius, then -50 degrees Celsius, but diesel keeps flowing, batteries hold charge, and the heated cabins remain a narrow band of life in an empty white world. No single design could survive this crossing alone. The Caterpillar hauls the bulk, the piston bully floats where others would sink, and the Unimog adapts to whatever the surface throws at it. Together, they form a system, each compensating for the limits of the others, each tuned for a specific kind of challenge. This division of labor is not unique to Antarctica. The same principles guide disaster response fleets in the Arctic and shape the chassis of planetary rovers rolling across Martian dust. The lesson is clear: survival in the harshest places is not about overpowering the environment, but about reading its signals and adapting step by careful step. In the end, the most extreme snow trucks do not conquer nature, they learn from it, and in doing so, they go farther than brute force ever could. Today, polar logistics still hinge on adapting to forces we cannot outrun or overpower. As climate extremes push infrastructure to new limits, the lessons of low ground pressure and engineered resilience shape how we respond, and not just in frozen wilderness, but wherever conditions threaten the systems we rely on. In the end, survival favors those who understand the landscape, not those who try to conquer it. Join the investigation. Subscribe for more stories like this.